Well, here's a few news articles. Let me get this resized to fill the screen correctly. All right. So I went to the Oakland Coliseum and I got my vaccine dose, and then they said we got the wrong amount because the syringes used have a possibility of not squeezing it all out. So you might get 0.2 milliliters instead of 0.3. Yeah, the vaccine didn't... I had a little bit of a reaction. Nothing big. My arm was sore. I was a little fatigued for a day or two. Then it went away, which is what you expect. So anyway, various people are getting upset about this. I'm not worried about it. All of us that went there, we had the typical vaccine reaction. And I know in Britain, they were thinking of giving half doses anyway. So if we got a little less dose than expected, it's not the end of the world. And we'll be going in there in a few weeks to get the next dose. So I think we'll be fine. But anyway, various people are complaining about it. I highly recommend this podcast, Sway. It is fantastic. If you listen to podcasts, you should listen to this one. It's the best one in the world. This is Kara Swisher, and she is the most famous podcaster in the world, I think, now. And she gets all the big shots on her podcast. She had Bill Gates. She has everybody you can think of. And she had Stacey Abrams, who is the woman that created the fantastic get out the vote efforts in Georgia that led to the Democrats winning Georgia, and therefore the Senate. And the Jim Crow Rebellion is 50 laws in Georgia and 150 all over the nation trying to make voting more difficult because the modern Republican Party has decided that instead of appealing to enough people to actually get a majority of the votes, their current plan for success is to just make it difficult to vote so that only the people that they like will vote for them. And that is... that's their current strategy. And anyway, she has a very good analysis of it and what to do about it. And so, anyway, that's a good one to see. Some of the Chinese people I know living in San Francisco are afraid to go out now, afraid to ride BART, afraid to leave the house because there's so much violence against Chinese people going on in San Francisco. Thugs are just beating up random Chinese people, sometimes to steal their money, sometimes to just punish them because they blame them for COVID, which is, of course, what Donald Trump wanted, calling it the Chinese virus and stuff. He feels that his supporters are bigots and like to perform violence against ethnic minorities, and therefore this is certainly true. And as I mentioned before, the current generation of Republicans is openly embracing bigotry and violence and the Nazi Party. They're all proud of those things, so it's working, and it is a tough thing. Old Chinese people around here are getting beaten up by random thugs and sometimes killed. So it's pretty outrageous. I also heard another one say that a bunch of people are having cars broken into, windows smashed, and garages broken into. So apparently street crime is very bad in San Francisco. It hasn't happened to me yet, but I'm not downtown, but it's apparently happening all over the place. And it's not a good thing. I tested the A&D Medical app and found I was able to eavesdrop on a username and password. Oh, with the broken SSL, you mean? Oh, by using Burp? Are you talking about an app on an Android phone? Because if that's the case, then that's very common. And the SSL is broken because an app chooses to use its own protocol, and they turn off the validation. This is very common because they want to be able to test their app, and they don't bother to configure a phone with a special certificate to do that, and then I think they forget to turn off the test version. So a lot of developers don't seem to understand SSL, so they turn off the authentication. Like I say, it seems to me like something like 5 to 10% of all apps have that flaw. There's a lot of them. And by the way, I'll tell you this, I learned from experience, if you try to tell somebody that it is a violation of HIPAA for a medical app to break SSL, they don't care. I tried telling a bunch of them, a whole pile of them, and they all say that HIPAA doesn't apply to them. So it's certainly a bad idea. And if you were a commercial financial app, you can actually be punished by the Federal Trade Commission for it. But medical apps seem to feel that they are not in legal jeopardy doing it. However, they might fix it. I found that sometimes people will fix broken SSL, but they don't take it very seriously at all, especially not medical apps. Anyway, it's worth extra credit in my class, doing it out of an app and sending in the results. But it's just a decision of the programmer to just not bother to test for that when they program their code. U.S. has put a couple sanctions on some other people in Saudi Arabia, but not their prince. The king is apparently senile and has no power, and the crown prince is ruling the country, and then he will become the king when the king dies, so he will rule for decades. And Biden promised to harshly punish him for killing that Washington Post journalist, but now that he's in office, he's doing the same thing previous administrations have done. They say, well, he's our ally, we have to have gloves off. This is why I know some people that imagine Donald Trump is going to prison, and the kings are above the law. Americans like to pretend this is not true, but kings are above the law in every nation. Donald Trump cannot go to prison, and MBS cannot go to prison. The way you punish a king is you take away a few of their toys. This is the way it always has been. But you can't send a king to prison. They are a higher life form, like a lion among the sheep, and they do not live on the same plane, and they're not subject to the same rules as us. It is a fantasy to think they will be. Realistically, Donald Trump will be punished by making him waste his time in court over his financial crimes, and perhaps by not being reelected and by not being able to get a bank loan. But I can't foresee any world in which he actually goes to prison anywhere, or that MBS goes to prison. But, they're punishing him by taking away a few of his toys, by bothering other people. It was encrypted before, but when I added proxy and checked, after the lecture, why don't you let me see that machine? And let me see. Probably what you're seeing is just that it was encrypted, but Burp does a man-in-the-middle attack that sends a fake certificate, so it's really re-decrypted. Anyway, let's see. It's time to start anyway. Good. So let me go down to the official stuff here. Close a whole bunch of these. All right, so we're at 129S, and here we are. All right. So today is session management. And let me bring up my slides. Yes, where did it go? Right, I hit the button and nothing happens. It must be sitting in the back somewhere. Right click, show all windows. Here it is right in front of me. Okay, good. All right, so all right, there we are. Now I can see the slides I was looking for. All right. So, session management is what's necessary to have authentication on web pages. The original HTTP protocol did not have any way to keep track of who's looking at the page, and session management is the system tacked on to keep track of who you are. So if you are able to attack the session management system, then you can change who the app thinks you are, get into somebody else's email, and so on. And this happened to me at the Wall of Sheep at DEF CON. I went there and logged into Gmail on the DEF CON network, and I thought I was fine because they used HTTPS. But at that time, Gmail used HTTPS only during the login process. Then it sent you a cookie, and then it sent the cookie without encryption. And they used a man-in-the-middle tool called Hamster and Ferret to steal the cookie, and then they could replay the cookie and get in my account. So I was on the Wall of Sheep. That's where they put you if they catch you at DEF CON and manage to steal your password. So anyway, this is the point. The original web was just like a bulletin board or like television. You would put up a page, and a bunch of people look at the page. They all see exactly the same page, and there's nothing custom about it. But the modern web, you have Facebook and Gmail and Canvas and everything where you log in, and after that you only see your stuff, not somebody else's stuff. So it has to keep track of who you are. And since in one way would be to make you log in again on every page, but that's ridiculous. So your browser automatically logs in on every page for you. And also, even without a login function, there are other things like a shopping basket that keeps track of the products you've chosen, and so on, where a web page somehow remembers what previous pages have done. And so you do it with a cookie or multiple cookies. The simplest way to do it is to just have a session cookie, which is hopefully just a random number, and that means there's a database on the server that has other bits of data attached to that session cookie. So you have a session cookie, and somewhere on the server that tells them who you are, or what's in your basket, or whatever other information they want to have about you. And so every subsequent request from the client will contain the cookie. You send it back with every request, so every request comes with a tag, which the web server can use to tell who you are. So if the session tokens are not random, or if they are somehow leaked out some way, then somebody else can get into your account by either guessing your token or predicting it or somehow stealing it because it's not handled in a safe way. So now a lot of automated session software products that people use on servers generate tokens, but apps don't really use it. So I've talked about this before. You can go into burp repeater and you can try removing tokens until you find out which one's actually used. Like here's a Cloudflare token, which usually isn't used by anybody. A DEF CON, if you used a VPN, yes, absolutely. Very good point. Sweet swear to. If I had had a VPN, they would have not have gotten my cookie. There would have been another layer of protection. I didn't use one, and they hacked into me. So that's why I've thought, I used to tell people VPNs aren't worth the bother, but I must admit that they will save you sometimes. So anyway, you can send something to a repeater and then remove the cookies or change them until it forgets who you are, and then you'll find out which one of the cookies is actually being used to identify you. So you modify it and send it, and you find out. So I went to Amazon.com, for example, and logged in, and the Amazon.com had a whole bunch of cookies. Session at main, SST main, session token, session ID, many, many cookies here, which of course, because it's very complicated, some of them are used to target ads, some of them are probably not used at all. And when I first did this, I was surprised to find that some of them are set encrypted and some of them are not set encrypted. And I thought I'd found a real vulnerability, but not really, as far as I could tell. So I discovered I could delete all of them except xmain, and it still knew who I was. So all those other cookies are not used to identify who you are, just this one. All right. So there are other ways to do it besides sessions. That sort of session, there's something called Basic Authentication Digest and NTLM. These also pass credentials, but they're not typically used on the internet. They're sometimes basic authentication, but these are mostly used on local area networks. So anyway, if the application doesn't issue session tokens, there's another way to do it. Now, the way I described is the best way, where the token I have is just a random number, and on the server there's just a database that knows what that random number means, because then nobody can guess my number and nobody can somehow figure out somebody else's number. But another way to do it is to encrypt everything where my cookie actually is encrypted or serialized data, like my username and things like that. And then the server doesn't need a database. It can just find the information it needs inside that cookie. And this is what ASP.NET's View State does. On your server, this is ASP code, you can create an array where you add items to it, and then you can create a view state from the array and send that to the client. And then every future request will feed in a view state, and you can unpack it to find all this information in there. So this is the risky activity I've been talking about since the first lecture, where instead of the server maintaining the data it needs, it sends it to the client and then believes it when it comes back from the client in a later request. So that means if it is not securely signed or encrypted, the client might be able to modify it and get the server to misunderstand the data. So you can put anything you want in this ASP view state, and it will just have this long string of base64 junk. But in the early versions, it wasn't secured, and in later versions, it's secured with a message authentication code. And it even is tied to your MAC address. So not only does it prevent anyone from modifying it, it prevents anyone from copying it and running it in from a different machine. Prevents a replay attack. So the modern versions, if you have these security features working, it's really quite strong, and then there's really no strong reason not to use it. It's just that the earlier versions lack these protections. All right, so if you have tokens that are more than 100 bytes long and you see a new item in response to every request, data is encrypted, and if you can't take it to burp repeater and repeat it, because you shouldn't really be able to, then you might that would be an indication of one of these sessionless state mechanisms where it's tied to your MAC address and so on. So there's various other ways to generate your token unwisely. There's a guy here that found a vulnerability on Facebook and got a $15,000 bug bounty for it. I think this one, what he did was he found that the token for a password reset included a random number that you could in fact find elsewhere. on somebody's page, so you could predict what would be sent them for password reset and get into their account. So this is what you use tokens for. Password reset tokens, the hidden form fields as anti-CSRF defenses, tokens used to remember me, and so on. There are many uses of tokens where it just tries to keep track of who you are, and all these depend on the token somehow being unguessable and unpredictable, so that me looking at my tokens does not give me the ability to guess what somebody else's token would be. So this is a meaningful token. This thing might look random, but it's just hexadecimal ASCII for this string. 75 is ASCII for U and 73 for S, and so it spells this out. So in that case, you could easily guess. If the username is Daft, I could just change the user to admin and figure out how to change this token. So that's the problem with tokens that contain meaningful data. All right. So in there you might have username, date timestamps, any variety of data might be in there. And so there are a lot of ways to encode data to put it in there. XOR, base64, hex codes. That one there was hexadecimal ASCII codes, which is just standard encoding of strings. All right, so if you want to attack a system, it looks like that's happening, then you can just take a token, put it in the repeater, and then start modifying it. Change 1 bit at a time or 1 byte at a time, see what happens. If it's a proper token, if you change anything about it, it will just give you an error message saying that's not a valid token. But if it's meaningful, then of course, if you have something like this here, I might change something about the date and that might not matter. So I'll find I can change stuff over here and it still takes it. But when I change stuff here, then I'm not getting in anymore. So that would be a clue that it's not really a properly randomized number. It's actually meaningful data. All right. And Burp has a thing called Charfrobber, which will automatically try to modify parts of the token. And so you might log in at different times at different users to see the tokens and then see if there's a pattern. It'd be nice if you can get a series of regular usernames. This is what I did when I hacked into Stitcher. Stitcher, the Android app, used to have simple Caesar cipher was their encryption. And so you could log in with a password of A and B and C and you just see it would be STU. It was ridiculously simple. And you look for correlations. Repeating letters often help. At Charfrobber, I don't think so. I've never really used the Charfrobber. I just use Python scripts and such, so I'm not really sure. But I imagine that the Charfrobber is probably, you need the Pro Edition. As you folks know, I think you can get a 90-day free trial of the Pro version if you want it. But I haven't really used it. I always do it sort of by hand. Anyway, so if you have repeating letters, and they're using XOR, then it'll create repeating letters at the other end. And if you're using base64, it usually ends in equals or double equals, which is a clue. You can also tell from the contents, base64 has uppercase, lowercase, and numbers, and then 2 punctuation marks, usually plus and slash. So once you've found some kind of pattern, try guessing the token of another user. And you can use Burp Intruder to send many requests and see if any of them load correctly. All right, let's try a Kahoot. Got him over here. Just drag him over here. And this is 129S 7A, which is right here. Good. Place to put winners. All right. Well, that may be all we have. Good. A few more is good. More than 3 makes a better competition. Good, okay. All right, I'll give it another few seconds. Okay. All right, so what encoding turns that into this? That stuff is base 64, uppercase and lowercase and numbers, and also every 3 characters of input turns into 4 characters of output, so it's longer. Anyway, that's what base 64 looks like. And notice this AAAA does not lead to repeating stuff over here, another characteristic of base 64, because this is using 1 byte per character, and base 64 only puts 6 bits in each character. So although this repeats patterns of 8 bits, the patterns of 6 bits do not repeat. Anyway. All right, what encoding turns it into that stuff? That's MD5. And by the way, MD5, you might argue it's not really an encoding because it's not officially reversible. But anyway, it's a common way people create a token. Anyway, and it always has the same length. So it's hexadecimal, by the way. This is not base 64. This is hex, because notice there's no capital letters and there's no letters higher than F. It's really just using 0 through 9 and A through F, not other characters. So you can pretty well spot a hexadecimal series and tell that it's not base 64. All right, how about this one? Okay, that's ordinary ASCII encoding. Capital A is 41, U is 75. You can tell this is US, STU, U is 75, and S is just 2 smaller, 73. This is just plain old ASCII encoding. That is how computers store English letters. So that's ordinary hex encoding. And how about this one? Yep, that's XOR, because the capital A's turn into repeated 05s, and the US turns into 2 numbers, but they're very much wrong. This is ASCII for 1 and ASCII for 7. So it's got a 1-to-1 match, and repeated characters repeat, but it's not just ASCII encoding. The numbers are different, so that's XORed with a fixed byte, so it scrambles the bits in each byte in the same way. Anyway, it's good to be able to spot those. It'll save you time. Isaac, that looks like a real name. Rick looks like a real name. Good. And Kunal is a real name. Good. So they might be able to give you points just based on that information. If not, let me know. Anyway. All right, let's take a look at some more of these slides. So, your tokens might be predictable from a simple pattern. If you have an old or poorly designed platform that you're using, it might be creating these things. I see Rick. Good. Rick tells me who they are. That's pretty close to the right name, but I'll make a note of the exact one. Ricardo. Good. Anyway, so if you gather a large sample of tokens, you might be able to do that by installing the same platform locally and playing with it. So here's Burp trying sequential payloads. Here it is trying just a whole bunch of numbers, 0, 0, 1, 0, 2. And as it tries them, it then notices the ones that are giving it 302 errors and not really logged in, it puts them to the bottom. And the ones that actually log in as somebody, it puts them at the top so you can spot them. So here's a token that's far too short. It's just a number, just 1 byte. And as it tries the values, it finds various bytes that lead somewhere. So that's an example of a predictable token where you can guess them. So here's common reasons why it would be predictable. It's either a concealed sequence instead of a real random number generator, or it somehow is dependent on the time, or it's a weak random number generation that has not enough entropy. Entropy is a measure of how unpredictable a random number is. And there have been quite a lot of flaws in computing where people have a random number, but it's not really random enough, since nowadays the processors are fast and the internet connections are fast, and you might be able to try millions of guesses. So here's a concealed sequence. This is really quite common. This looks random, and if you just decode it as ASCII, it will just be unprintable, random-looking gibberish. That's why a lot of people make random number generators like this, where it looks pretty good, it looks random, but it's in fact not that random at all. If you just turn these into hexadecimal numbers, then you will notice nothing obvious right away, but now if you take the difference between them, you'll see a pattern. They often have exactly this difference, 97C4, and or it's this, which is just wrapped around for negative differences. So this means these are actually just counting up by a fixed amount. It's like, and then keeping the lower number digits of the big number created. So this is actually just a straight line, and you're taking those numbers and just throwing away the high order bits. So it looks random, but it's not random at all. And so you can easily write a code that will just predict those numbers from the first one. So that's pretty obvious. I mean, it will just calculate tokens here. You just add that number every time. You start from 1, and then you just add it in every time and just throw away the high order bits, and you get that pattern of numbers. That's called a linear congruential random number generator. It's often used, but it's not very secure. The random numbers are actually predictable. And here's another token. Notice the one on the left just keeps incrementing, 38, 39, 40, 41, so that's easy to predict. The one on the right, a whole bunch of it never changes. And the stuff at the end changes, but it's always going up, and it's not going up that high. Here it went up by 300, here by 200, here by 500, here by 300. So it's just jumping up by a few hundred every time. So both of them are not really that hard to guess. And if you wait 10 minutes and get another sample, then you'll see the first number is jumped by 6, and the second number is jumped by about 600,000. So the second one just looks like it's the time, 600 seconds, 600,000 milliseconds. And the first one is just like counting the number of users that have registered accounts. So that means it's pretty easy to predict somebody's token. Just wait until you see it go up by more than 1, and then you know there's another user in between, and now you know the left number is the number in between, and the right number is between the other numbers, and only a few hundred guesses, so you could predict somebody else's token pretty easily. All right. So here Jetty is a web server that generated these things with a linear congruential generator. Like I say, it just multiplies the previous number by a constant, adds another constant, and keeps the lower bits. So once you have one value, you can predict all the rest, because it always uses the same number to multiply and add by. So this is what it does every time. All right. And PHP had a similar vulnerability. It used just these things, the IP address and the number of microseconds the machine has been on, and the time, and a linear congruential generator. So it took a lot of things and put them in the token, but none of them are really very random. So it sat around for about 10 years until Sammy Kamkar, a very famous hacker, actually wrote a tool that would attack it and break into PHP tokens that way. So anyway, that's the problem with randomness. Defining how random something is can be a difficult statistical problem. So here's the way you test randomness. Assume that these things are random, and then you apply a test and decide what the probability of this thing happening if it's random. And if you manage to get a situation where some kind of pattern is observed that is very unlikely to happen if it was really random, then you can say it's not random. And Burp has a thing called sequencer that will try to do this. You tell it what part of this you think is random. It will then get a bunch of values by sending a lot of requests and then see how much they vary. And here you got what is the probability of this happening if things were random. And here it's 0. So these ones were the same every time. These bits it looks like a 64-bit value. Some of the bits were always the same. So that's a failure of randomness. Some of them were nearly almost the same, and some of them were pretty random. So that's what happens. All right. That's one way to measure how good a system is. So here's your design goal. If you want to do this, where you're going to take meaningful content and encrypt it, then this might not be as secure as you think it is. A lot of people believe that if you encrypt something, the encrypted data cannot be used at all unless you have the key and you can decrypt it. But that is not true at all. It depends on what cryptographic system you use. The most dangerous and a very common choice is electronic codebook. This is classic encryption that people learn in a math class, where you just encrypt one block of data, and if the data is longer than that, you just keep encrypting blocks individually, not depending on each other. The problem is, if 2 blocks of input data are identical, the 2 blocks of output data will be identical. So that means if you encrypt something like an image, the white will turn into this funny color, and the green will turn into that color, but a solid block of green will just turn into a solid block of some other color. The large-scale patterns are still preserved. So this is not what you expect from encryption. This has not scrambled it so you can't see the pattern anymore. It's just kind of blurred it. So here, for example, is a token with several meaningful fields, and here's the encrypted form. It's encrypted with blocks of 8 characters, another 8 characters, another 8 characters. Since there's no repeating block of 8 characters in this input, then there's no repeating block in the output. Yeah, that's Cloudflare. Yeah, Cloudflare has a wall of lava lamps. And that's what you do. If you really want random numbers, you set up some system that is really random. By the way, modern Intel processors have a hardware random number generator that runs an electric current through a resistor that varies from the random motion of the atoms and is intended to generate high quality randomness. So here you take this login, it breaks it up into blocks of 8 characters, and then you make them here. But see, you can still hack this even without the key, because since the blocks are independently encrypted, you can shuffle the order of the blocks. So here I had a line that had 992 semicolon in it. So if I put that line down here, just repeating that encrypted data, it will decrypt into UID equals 992. Now I used to be UID equals 218. That was the account I registered. But by just scrambling these blocks of encrypted text, I will eventually reach a situation where it reaches a different UID. Yeah, that's right. RSA keys in OpenSSL, you have to move the mouse to create randomness. Yeah, that's the issue. Getting enough randomness is really quite a challenge in computing. Anyway, so now you can, and by the way, if you make a user with the right name, like DAF1, then this wraps around so you have a line with a 1 at the start, and you can put that line up here, and now your UID equals 1, which is usually the root account. So even though you don't have the key and you're just manipulating the ciphertext, you can sometimes still create meaningful combinations. So the cipher block chaining is considered the standard secure technique, where to prevent that attack I just described, you take each block of data after you encrypt it, you take that and XOR it with the plain text before doing the next one. Take the output of this block as the semi-random number to XOR the next plain text with. So now, even if all the inputs are exactly the same, the output will keep varying randomly. So it prevents that problem of preserving patterns, and it makes an encrypted image turn into just random snow, so you can't see anything. That's why people think it's much more secure. But it has a weakness too. And, all right, so here's CBC. If I encrypt this data with CBC, again, it looks completely random. But the thing about CBC is when you decrypt it, I feed in the encrypted stuff and you decrypt it, and then this ciphertext is XORed here at the end. So if I change 1 byte of the ciphertext, then I scramble this whole block of data into random junk, but I change only 1 byte here. So if you have something like a web request that probably has a series of parameters, and some of those parameters do not matter. Like, remember that Amazon request I started with, where there were about 10 cookies, but 9 of them don't matter. So it was perfectly fine for me to sacrifice a large portion of that request and turn it into random junk. It won't matter. But I can actually control 1 byte at a time here, so I could find the byte that determines who I am when decrypted, and I could move it by just a little. And then I might find my way into somebody else's account, or elevate myself to administrator by changing something from false to true, things like that. So you can now create altered values. And here's what you might find. As you alter things, the question marks are the unprintable characters. So there's a bunch of collateral damage, but this number changed to 8. This number, it should have been 7. This number changed from 0 to 2. This letter changed from P to Q, and so on. So you just change random letters and send these requests, and eventually one of them is changing this number, UID, the one that matters, from 216 to 226, and then you're getting in somebody else's account. So just changing 1 byte at a time and recording the results can be enough to overcome any of these encryption schemes if they aren't implemented carefully. And a lot of people do not understand cryptography. They just turn on some kind of default operation and trust it. So get a session token, and then you modify it, and there's a thing in burp intruder in payloads where you can just flip every bit. So flip 1 bit, flip the next bit, flip the next bit, and try all of those. And it will then not take that many requests, 8 requests per byte. So, this one here had what looks like about 100 bytes. So it'll take about 800 requests to just try flipping a bit everywhere. And when you're done, you'll see what happens. And here's DAF is the original user. There's unknown users. And here's a couple that turned in other people, Peter Wiener and Josh Harmon. So, there's that's the thing. These are the ones where that 1 bit you flipped happened to change the one number that mattered to determine who you are. All right. Another thing that might happen is even if your application uses some kind of strong encryption where you can't use one of these simple attacks, there might be some way to find out elsewhere in the app where I can get it to use the same encryption engine, like to create a download link for a file or something like that. So I might be able to trick it into encrypting this phrase UID equals 1 or something somewhere else in the app. That often happens because you just sort of get confused as you keep adding new features and reusing code, and eventually you reuse code that some other developer thought was sensitive and only intended to be used for one purpose, and you use it for some other purpose. All these problems really come from sort of disorganization and chaos at the other end. What do I mean by generating? No, that's if you run OpenSSL and generate a RSA key, then it'll often say you have to move the mouse. It'll make you move the mouse and wait while it builds up enough entropy. It's something a lot of people have seen. I haven't seen it that much lately. They may have changed that, but it was a common issue. Last time I ran OpenSSL, it didn't do that, but this is something some people remember seeing. Another thing that happened one time to me is I had a Java-based server and it took 45 minutes to boot up, and I had to install an app that just creates randomness because when it boots up, it needs some cryptographic keys, and it was unable to to boot up until it had enough randomness. So I had to install this thing called havejed. All right. In a cryptography class, we even try watching the size of the entropy pool. You can actually run a command to see how much entropy there is, and you can change it, and you can use it up. You can only generate so many random numbers before your computer runs out of randomness. I'll give it a few more seconds. All right. CBC also vulnerable to padding oracles. Yes, the padding oracle attack is based on the same weakness, that you can change 1 byte at a time of the output. Yeah, and we do that in the cryptography class. It's a good attack. All right, so what system makes replay easy? Okay, yep, if you encrypt meaningful data, then you might be able, then you can just replay that same data later because it probably is lacking randomness anyway. All right, what system can you exploit by rearranging blocks of ciphertext? The electronic codebook is one where every block is independent, so you can rearrange them and it will still be valid. All right, which one do you exploit by changing a single byte? All right, that's cipher block chaining. Yeah. All right. And which one uses one block of data to influence the encryption of the next block? Yeah, that's cipher block chaining again. All right. Let's see the winners. All right. I know who that is. And I think I got a record somewhere of who that is. And I know who that is. All right. Good. Well, I'm going to stop this recording.